Hello, chemists. It's Mr. Gopal here with another lesson from the Oxidation and Reduction Unit of Regents Chemistry. Specifically, we're here to learn the purpose and composition of Voltaic Cell. We got a head start in my previous video when I discussed how to balance redox reactions. So if you recall, in a redox reaction, we have two elements, all right, that need to be balanced, and there are free floating electrons traveling from one to the other. The one that loses electrons is said to be oxidized, while the one that gains electrons is said to be reduced. Now, I've packaged all this together in a handy handout for you, all right? So as I said, oxidation is the process of an atom losing electrons in a chemical reaction, and this transforms it into an ion with a positive charge because it has more protons than electrons. These positively charged ions are known as cations. Reduction is the opposite process. It's the process of an atom gaining electrons, and so its net charge will be negative because it has more electrons than protons. These ions are now known as anions, right? And the redox reaction, as I said before, it's a chemical reaction in which one element is oxidized, it loses the electrons, while another is reduced, okay? And before we talk any further about the Voltaic cell, all right, I'm going to show you a picture of it. So several things are going on in this simulation. It's very helpful, all right? First of all, I want you to look at the very top of the simulation. We see a light bulb and we see current being passed through it. As you can probably imagine, if this were a real life situation, we would be able to power this light bulb. But it seems kind of crazy that we're able to power this light bulb with two metals inside a solution connected by this upside down U type of thing, all right? I'm going to label each of these, and then I'm going to go back to the handout to show you a little bit more about how to think about this. There's a lot of terminology in this unit, which is why it was so important to me that I provide you with some vocabulary and also an active illustration, a simulation, in other words, all right? So we can see that electrons are flowing from the left-handed terminal to the right-handed terminal, all right? What's going on here can be broken down into several steps. For one, zinc has a lower electronegativity than copper, all right? And we also know from one of the first units that we studied that metals are good conductors of heat and electricity. In this case, they're conducting electricity, so there's no problem for the copper ion or the copper piece in the right-handed terminal to attract electrons while the zinc one loses them, all right? Now, as the zinc one loses them, what is going to happen is that we have a zinc ion solution, all right, that is net negatively charged. And because it's net negatively charged, the resulting positive charged or cations from the zinc bar end up migrating into the solution. And that's what's happening over here. So we can see here repeatedly, as we lose electrons, we create a positive ion on the metal piece, all right, in the left-hand terminal. And since the zinc ion solution is negatively charged, the zinc wants to migrate there because atoms are always looking for stability, okay? The opposite is happening in this one. We have a positively charged copper ion solution. This should say copper. The one mistake in the simulation, they misspelled copper, all right? We have to deal with copper. But the principle is correct. If I have a positively charged copper ion solution, all right, and electrons are navigating into the copper bar in the right-handed terminal, all right, then those ions are going to want to flow into there. Again, we're achieving neutrality by complex means. Now, we just need to talk about what this thing is in the middle. This is the thing that sustains this electrical current, all right? If we didn't have an electrical current, overall, we would be reducing the size of this metal bar, these metal bars over time, and we would end up with a charge imbalance. There would be all this electron flow onto the right-hand side, resulting in an imbalance, all right? There is always an imbalance in the ion solution. It's because it's an ion solution. However, given that there will be spare positive ions flowing in and imbalancing this on this side over here, and there will be spare positive ions flowing out into the metal bar, and imbalancing this to the negative side over here, we need something else to balance it all out. This right here is the salt bridge. If you recall, a salt bridge is made up of sodium chloride, all right? Now, thinking back to when we studied groups and families of the periodic table, sodium is an alkaline metal. That means that it's in group 1. That means that it has 1 valence electron in its outermost shell. So it has low electronegativity, and it is perfectly willing to give up that electron, all right, and become Na+. On the other hand, chlorine is a halogen. It's in group 17, right, which means that it has 7 valence electrons. It is 1 shy of the octet. It really wants another electron. So it is willing to become Cl-. As you might have predicted, this salt bridge acts as spectator ions. What are spectator ions? Well, on this side, they would be Na+. I'm going to do that in a different color. On this side, they would be Na+. And on this side, they would be Cl-. Okay, and the reason that works is because we have this positive ion flowing out here, and it will be met by a negative ion flowing into it, all right? Achieving neutrality. Over here, we have a positive ion flowing out, so we have a net negative charge happening here, but that is flowing into the positive ion charge. We call these spectator ions because they spectate, meaning they wait for the current to start flowing and the imbalance to start happening. And as soon as there is imbalance and instability, these ions will flow in, maintaining neutrality and allowing there to be a current flow without a severe imbalance, also known as a junction, occurring. And this allows this thing to continue to pass current from the left terminal to the right-hand terminal. Now, that was a fast explanation, but don't fear, I have everything mapped out in diagrams for you. So we have definitions of all of these things, all right? In addition to anode and cathode, I'll go back and define those really quickly. Our anode is our left-hand terminal because it is an electron donor and it is net positive. It's our positive terminal because electrons are being passed away as the zinc oxidizes, all right? Our right-hand terminal, that is our cathode terminal because it is an electron acceptor, and is our negative terminal because our copper ion continually becomes negative, all right? Then we have the salt bridge to balance out the change that is happening from the ion solution on either side, all right? So that we can maintain neutrality and keep this thing going. So it's rather brilliant. This is called a Voltaic cell. It's also known as a galvanic cell, and the names are after 2 different scientists, 2 European scientists who discovered the principle at work here. So in other words, we can use a redox reaction, i.e. we can oxidize one element while reducing another. And as long as we have solutions, aqueous solutions, mind you, then we have the conditions that are proper to allow us to pass electrons from one terminal to the other, creating something like a battery. Finally, I have a diagram here with the whole thing worked out. All right, so galvanic cell, also known as the Voltaic cell, will convert the chemical energy from a redox reaction into electrical energy. In other words, they act like a battery. I have the 2 half reactions set up, and they correspond to the 2 half cells. This is one half cell here. This is the other half cell over here. All right. Now, since we know that, we can see how the salt bridge balances out the difference between these 2 half cells, all right, that's created by the passing of current. But it is crucial that these are dipped into an aqueous solution. If these were dipped into dry ZnSO4 and CuSO4, it would not work. We need an aqueous solution in order for there to be a reaction and for ions to pass into it. All right. Finally, again, just to review this, we have built up to this through the various units that you've studied previously. So we understand tendencies of metals and nonmetals. as respectively electron givers and electron acceptors. All right, and we also understand that zinc has a lower electronegativity than copper, therefore it is going to pass the electrons. We also know from our early studies that metals are good conductors of electricity. And finally, we know that Na and Cl are in extreme positions on the periodic table, which means that they're ready to become ions. All right. All of this contributes to something beautiful. Now we're able to convert chemical energy into electrical energy. So I hope this is a helpful breakdown. If we look back at the unit, it's pretty cool, meaning they have a video of this actually taking place that you should definitely watch, all right? But they don't cover it in great detail. So it can be hard to pick up every last thing. You don't need to understand it on the level that I did. So they did a very good job. You don't need to understand it on the level that I did. But the first time that I studied a voltaic / galvanic cell, I was a little bit confused. And so I needed to walk myself through every bit of how the chemistry works. Now it all works through charge imbalance. Through charge imbalance, we are able to create electrical current. And that indeed is a fantastic thing. So I hope this is very helpful for you. And as usual, I will see you soon.